All right. Yeah, thanks for the reminder. Okay, let's see if we can get this started. Okay. Look. Okay, so we're nearing the end of the semester, but there are a couple of interesting things to still go through. And so welcome to our 12th lecture on deep learning. And so just the recap from last week. So last week we talked a lot about unsupervised learning, or we introduced the idea of unsupervised learning. And so one of the main things that we discussed is autoencoders. And so we had two variations of the autoencoder, the standard autoencoder, which is more, best thought of as kind of like a compression, right? So where you take some high dimensional data, you're trying to represent it in a much lower dimensional space. And then you, in order, if this is a good compression, then that means that you can recover at least approximately the original data from this compressed version. And then there was also the variational autoencoder, which is a little bit more statistically motivated and also has a few interesting properties. And so I just wanted to review these quickly. And we also didn't really talk yet about how to build kind of concretely a variational autoencoder. So we'll do this. And then in the second part of the lecture, we're going to talk about generative adversarial networks, which is one of the kind of first things that really blew people's minds in deep learning. Okay, so building VAEs. So we kind of derived this general idea behind the variational autoencoders. And so there are kind of two perspectives that you could have when you're looking at a variational autoencoder. So there's this first principle derivation from amortized variational inference using reverse KL divergence and the evidence lower bound measure, which is the elbow. And then we can also look at it as kind of like an ad hoc regularization. So we started with the autoencoder, and then we see, okay, that it has like a few properties which you don't like, and let's just try to fix them, right? And so we didn't discuss how to build them, so we'll kind of review this quickly, and then get more into the mechanics on how to build the variational autoencoder. And so I'll go through this quickly because we discussed this in detail in the last lecture. So the idea, the first principles perspective is that we start, okay, we want to do unsupervised learning, which means that we want to somehow describe the distribution of data P of X. And so in order to build like a good model of P of X, what you do is like maximum likelihood estimation. So if we could, evaluate P of X, what we would do is we would kind of take like a family of models that is parameterized for different parameters. We can calculate P of X, and then we would shift the parameters in order to maximize the log probability for the data that we have in our data sets. So that would be a very simple unsupervised learning technique, but we cannot evaluate P of X. And so we derived a lower bound, at least on P of X, which is this elbow. And so this is basically an expectation value about the of the joint, probability divided by the posterior. So actually, this should be log probabilities. So let me just try to fix this. Okay. Okay. On how well we can reconstruct the data given any latent code. And so this is termed the reconstruction code. And then this second term is actually, if you look at the definition, it's basically kind of like a KL divergence in itself. And what it does is basically it compares the posterior, so, how sure are we what the latent code is given the data, with the prior, right? And so if we have a very powerful encoder, then there's going to be a big difference. So the data is very informative about what the latent code is going to be. If the decoder is not, or the encoder is not so great, then, this KL divergence is going to be low. Okay, so we can basically write it kind of in this format as well. Okay, so then once we have kind of this elbow expression, we can kind of assume a certain type of target latent distribution that we want to achieve, right? And then we can learn, all the components that are needed in order to do this. So we had basically this inference network, which is the encoder part, but in this more statistically motivated picture, it's like an inference network. You're inferring what the true latent code is, like a low dimensional underlying truth, given like a high dimensional image. Is okay, we want to adjust the inference network and the reconstruction network to basically maximize our log probability, right? But then we said, okay, we cannot access the log probability, so we're maximizing the elbow, or basically, okay, if you say, okay, you minimize the negative elbow, and then you can, get a loss term like this. So I'll not go through this in detail because we discussed this at length in the last lecture. But the idea is that if you maximize the lower bound, you're also implicitly maximizing the log probability, because it will always need to sit above the elbow. So the bigger you can do the make the elbow, the bigger your log probability is, even though you cannot compute it. Okay, so then when we actually want to go and build a variational autoencoder, we need to somehow specify what these parameterized families of densities should be. So this is kind of like the same idea that we use also in normal inference, where you have like this, wrapping vehicle of a standard density, like a normal density or Bernoulli, and then basically the neural network part really comes in the sense that we are predicting what the parameter of this wrapping distribution should be. So for the inference network, what we are saying is, okay, let's assume my posterior is like a Gaussian, right? So, okay, I know it's a Gaussian, but I don't know what the kind of expected latent code is, and I don't know, how broad. And so you basically just assessing, okay, can I get close to the original image, right? But underneath this simple expression is like a statistical story. Okay, so this is kind of like the first principles perspective. There's also like the regularization perspective, right? So the standard autoencoder, we only train purely on the reconstruction. So this is the only thing that an autoencoder needs to do. It just needs to be able to reconstruct the thing. We want to map the data into a low dimensional space and then decode it, and then the reconstruction should be good, right? But then if you look at the and we motivated this using like an upper bound on the mutual informations. But then if you look at a variational autoencoder, the loss looks a little bit different. And so what is different? So there's really two key differences to the VAE loss compared to the autoencoder loss. So in the autoencoder, without variational autoencoder, there's a deterministic mapping from the data to the code. I'm compressing the information. And then there's no KL term, right? And so what's interesting is that you can kind of think of these two things as both. Now when you go from autoencoder to variational autoencoder, we are basically adding, we make the encoding stochastic, and then we add this KL this decoding, is going to produce crap, right? Because there's no reason why this should be like a smooth latent space. But if we're now resampling, so let's say we're doing a code and then we perturb it a little bit and then we decode and we still, require that this is going to be a good encoding, this kind of noising operation is going to encourage that kind of, it's like a smooth decoding. Even if you kind of get the code a little bit wrong, it's still supposed to decode successfully. And so with this, you're basically ensuring or encouraging smoothness in the latent space. And so we've seen in the original image with the autoencoder, becomes very unruly. And so there's no kind of nice regularity as with the variational autoencoder. And part of this is because there's nothing that is controlling the regularity in the latent space. So you can have a lot of like sharp edges. Term, what is it measuring? It's measuring how well are you, how well is your inference? How sure are you about the latent code? So imagine if you're saying, okay, I have some data, I want to measure something, and I have some prior, like in standard Bayesian analysis. If the data is very, very informative, there's going to be a big change between the prior and the posterior, right? Because the data is very informative. And so the scale divergence is going to be large, right? Because the two densities are very different. The data impacted your beliefs quite a bit. But if your inference of the data is not so informative, then this inference is going to be maybe only change your prior beliefs a little bit, and so the difference between prior and posterior maybe isn't so large. And so basically the question is, okay, given like a datum X, how much can we infer the code? And if the data is very informative, then we're kind of on the very right hand side. And if you cannot, if the latent code is not predictable at all from the data, then basically your prior and the posterior are the same thing, right? And so there's a little bit of a gradient here to the extent of how well does your very good inference procedure, have like a very big difference between the individual posteriors and the priors. What we can do is now, let's say we have like a collection of data items. So what we can do is we can look at what is the empirical distribution of latent codes, right? So this is what we had also with the scatter plot. So we could just take our data, we produce all of our kind of posteriors for each of these data items. And now we can see, okay, what is like the overall expectation value of latent code? What is the distribution of latent code? And so there's a kind of obvious effect that if you cannot, infer at all what the latent code is, then of course the distribution of latent code is going to be exactly the posterior. So for every data, your posterior is, P of Z basically, then the expectation value of this posterior under all of the different data items is also just going to be basically, P of Z. And so if your inference is horrible, then you succeeded very nicely in making the latent code very smooth because it's just going to be a standard normal distribution. So that's great. So you have a great latent code. The problem is if you cannot infer Z, you will not be able to reconstruct. Okay, so basically having this KL divergence in the loss. So actually what we're encouraging is the left-hand side. So we're encouraging more overlapping things because we want to kind of shape, we want to encourage that the latent space looks roughly like a Gaussian, but it's going to be at a cost of reconstruction. And so what the VAE basically has like this little piece that encourages a nice shaping, and there's a separate piece that is responsible for the reconstruction. And so these things are basically kind of in competition to each other. So there's one thing that is encouraging to go to the right-hand side, which is the reconstruction term in the VAE, and then there's a term that is encouraging to go to the left-hand side. You have like a bit of a game or competition while you're optimizing these networks. Okay, so then from this regularization perspective, there's really no reason to jump through all of these statistical hoops, and we can kind of ignore like elbow and all this thing. You can basically just say, okay, I want to have very good reconstruction, and I want to have a nice latent space. And so these two things are kind of opposing to each other, so they enter. You want to regularize. So you can say, okay, I'll just do like a standard autoencoder. I just have reconstruction error, and then that's going to be it. And now you start, okay, I want to fix it a little bit, or I want to fix it a lot. And so typically what you have is you have like coefficients for these regularizing terms that allow you to control, okay, how much do you want to fix the problem, and how much do you want to encourage like a nice latent space at the cost of a good reconstruction. Okay, so this is basically the relative importance. And so this kind of trivial addition of adding like one coefficient is already a new network architecture. It's called a beta VAE, right? And so the reason why it deserves its own name is because people observed if you have like you encourage a lot of regularization, what happens is that the encoder will basically encode in the latent code the super high level things. Like it can figure out about the image, and so that it can at least like roughly reconstruct, right? So you can say, okay, the low level, the pores of your skin I mean, you might not have a very good reconstruction if you don't, reconstruct the pores of the skin. But if you get the skin color wrong, that's the catastrophic failure. And so if you're, already, figure or get like latent factors that have semantic meaning. And so people, once you go to beta larger than 1, which would be the standard VAE, so a beta like 2 or so, you basically see that you have independent factors that control the skin color and age and gender within the latent space. And so this is nice for things like interpretability. You can look into the latent space and see, okay, this direction corresponds to skin color, this direction corresponds to age. And so this is kind of nice because it allows you to understand what the latent space means. Otherwise, this is all up to the neural network to figure out. And so there are lots of work to find what's called the disentangled representation, but interestingly enough, just kind of pumping up this beta value already does the trick to some extent. Okay. So now, let's see how we can basically build a variational autoencoder. So we have these competing interests. So we're trying basically to play a game. You're trying to increase the reconstruction, but this is going to mess up the latent space. And then if we try to fix the latent space, it's going to mess up the reconstruction. But so let's see how we can actually build this. And so the really kind of key problem in variational auto comparing our prior P of Z with our posterior QZ given X. And then we have our reconstruction loss, which basically takes the data and the decoded mean values and basically computes like a likelihood between the two things. And then we add these two things together, and that's our overall loss. Right? Okay, so this already looks a little bit more complicated than the standard autoencoder, but really the big problem here is the stochastic operation here in the middle. And so basically what we want to do, if we want to learn, we need to backpropagate our gradients, right? But going from like a mean Z value and sampling a new Z value, this is a discontinuous thing. So you go from one thing, you jump to a different Z value, and this is a non-continuous operation, and so you cannot propagate gradients through like a stochastic operation like this. And so this is a big problem because now our backpropagation is broken, and this is usually how we train our neural networks. And so let's try to fix it. Of course, I wouldn't talk about variational autoencoders if we couldn't fix it. Okay, so let's how do we fix it? Basically, what we're going to do is, okay, let's okay, so what is the trick? The trick is going to be that we're going to outsource our randomness. So instead of having our random mapping kind of in the middle of this entire computation where it's hurting our back propagation, we're going to externalize it and have it as a separate thing. So we will take the randomness out of this basic operation path, and then it's only going to be, so the randomness is like in the epsilon, which we sample separately, and then we have a deterministic mapping from C will be a function of B and noise. So there's still going to be noisy mapping from B to C. So you cannot deterministically predict C once you know B, because you have like this noise component, and this will vary the C independent of B, right? And so you still kind of effectively get this stochastic mapping, but somehow like between D and A there's now only deterministic mappings, and so this will fix our back propagation. So we'll go through this in a little bit more detail, but so these are basically these two options, before and after. Okay, so let's look. So this is called reparametrization, and so machine learning people like to call fairly simple mathematical operations tricks, and so they call it the reparametrization trick. Okay, so let's see what they mean with this. So let's say we have our standard normal, like some standard normal random number, right? So it's 0, 1, and so this is just some noise. And so now let's say, okay, we're computing a function of the noise, and so for every random epsilon, I'll get like a random y, right? And so now you can say, okay, y is now also just a random number, and you can think to yourself, okay, what is the distribution of possible y values, right? And of course, it depends somehow what the distribution of epsilon is, but it also depends on how you go from noise to y. So what is this function f of epsilon that gives you y, right? And so the way to do it is basically you can make an integral, you integrate over all possible epsilon values, and if you want to say, okay, how likely is a specific y value, you just sum up all of the probability that produces a y value. And the way that we do this in an integral is we have like a delta function, and we'll basically vacuum, like scoop up all the epsilons that produce this specific y value, right? And so this is kind of how you do this. And so now you can, so this is the distribution of P of y. Okay, that was easy enough. Now you can say, okay, what is the expectation value of a function of y? And so the way we do it is basically, okay, we have an expectation value of a function of y over, as the expectation value is taken over the possible values of y. And so now we basically say, okay, we have an integral, we integrate over y, we have our function g of y, and then we weight it with the probability of y. But now we know also what the probability of y is. It's just this additional integral with delta function. And now the trick comes, basically, okay, we can just integrate out y, right? Instead of integrating out epsilon, we integrate out y. And now it looks like this. Basically, okay, if we integrate out y, we need to replace every y with f of epsilon, right? Because the delta function will force it to be f of epsilon. Okay, so now basically what you have is you have an integral over epsilon g of y, but we know y is f of epsilon, and so we have g of f of epsilon times p of epsilon, right? Okay, so what we've achieved, so this is what's called reparametrization. We can rewrite an expectation value over y as an expectation value over random noise if we know how to convert the noise into the y's, right? So if we can reparameterize like standard noise epsilon into whatever random number we're interested, which is y, then we can go back and write that expectation value over this random variable y as an expectation value over the random noise. Okay, great. So this is the reparameterization trick. It's 2 lines, but actually it has a big difference when training variational autoencoders. Okay, so then let's use this in our variational autoencoder. We have our so in the variational autoencoder, there are lots of terms that basically take the expectation value over qz given x, right? So we have some expectation value over z, and then so this is our latent code, right? And then we want to decode it. And so there's some kind of function, loss function that is a function of the latent code. And so what we can do now is, okay, we can basically, say, okay, we want to say, okay, let's say we can compute Z as a function of epsilon, then we can rewrite this expectation like this, right? And but at the same time, so we know, that our, the possible Z values should be somehow determined by the mean latent code and the sigma, right? So because we want our Z's to be conditionally distributed around mu with sigma. So we're not saying, okay, Z is just purely a function of epsilon, so it's going to be a function of random noise and this conditioning information mu and sigma, right? And so now when we say this, basically what is effectively happening through this reparameterization, okay, if we have random noise, this is basically mapping this, imagine you have like a fixed mu and sigma, it's, effectively mapping it into a distribution, like a conditional distribution of these given mu and sigma, right? And so, the epsilon is kind of responsible for making this, probability density, and then the mu and sigma are responsible for making this a conditional probability density. Okay. So now then the last step is, okay, so we know that these parameters of this conditional density mu and sigma, they actually are functions of our data, right? So we're encoding our data into like this QZ given X, right? And so we know mu and sigma are a function of X, and so our reparameterization gets a little bit more complicated. So the Z is a function of this mu and sigma, which are functions of X. And then because Z is a random number, it needs a little bit of randomness injected to it in order to not make it fully deterministic, right? And so what you now basically have is you're basically mapping a random, like a standard fixed density over like just pure noise to like this family of conditional probability densities which is parameterized by phi, right, which is our kind of neural network. Okay, so now we almost arrived everywhere, and so we can now kind of look into what this is. So we have kind of our expectation value, which is where we sample the latent codes given the conditional distribution that we get from the encoder. And so the way it looks like is now, okay, we have our X, we stick it through a neural network. With this, we're predicting mu and sigma, right? And then, so this is parameterized by some phi's. And so now that we have mu and sigma, we say, okay, now we want to sample Z, which means just, okay, let's take this and then stick in some noise, and then we'll get our Z, right? And then we can go on and compute whatever function, loss function we want, right? And so now we have all of this, but so if you kind of zoom out a little bit, basically what it looks like, it just looks like a neural network that has two inputs. It has like the X, and then it has some noise, and then it will produce the loss function, right? Or it will first produce the Z by kind of mapping into the mean latent state and taking the noise, producing Z, and then you can compute X, some kind of loss function. Okay, so then once you have this reparameterization, it really looks more like a much more standard neural network, and it doesn't look complicated anymore. And there's no doubt now that you can backpropagate from Z to phi, right? Or from G to phi. You can backpropagate now through Z, which was the problem before, because we kind of outsourced this randomness. Okay, so now we have a very simple procedure for VAE training. So we're basically saying, okay, we sample a mini batch from our training data. We have, like, say, our images, and now we want to run them through the encoder, and then sample a new latent code, which is kind of this resampling, and then decode. And the way we're going to do is we sample a mini batch, then we also sample some external noise, which we're going to use kind of a bit down the road. Now we compute what our conditioning information is for our latent code distribution, mu and sigma. And now we take our mu and sigma and we take the noise. So for every image, we have a bit of noise that we kind of pair with it. And now we use that to compute Z. And then we can decode it with our decoder. And so this is very much differentiable. and you solve the problem of VAE training. Okay, so there's one more thing that's kind of interesting VAE training. So if you look at the KL divergence term, right? So KL divergence has exactly this structure as well, right? So, but both the reconstruction term and the KL divergence term have this shape. So if you look here, oops, let me see. So the reconstruction term has the structure where we have Z sample from QZ of X, but the KL divergence term internally has the same structure. And so you can say, okay, we know how to do these expectations of these resampled latent codes, and so great. We'll also compute the KL divergence term with it, right? So because we could expand the KL divergence as this expectation value over Z and so on, and now we can rewrite it as an expectation over epsilon. But this is always going to be a very like a stochastic estimate of this KL divergence, right? Because we cannot really compute like the expectation value in closed form, but we'll sample, like an epsilon, and then on average it's going to be all right. But it's not really necessary, right? We don't need a stochastic estimate, because once we know what the density QZ given X is, if they're both Gaussians, we can just solve this KL divergence term in closed form, right? And so we don't need the noise to compute the KL divergence. And so this reduces the variance a lot. And so this helps stabilize the training. And so if you implement the variational autoencoder, you can start, trying to implement it like this, maybe educational, but then if you actually want to use it in production, usually people compute the KL divergence in closed form, and later on, this is also going to be the trick for diffusion models. Okay, so this was the variation autoencoders, and so I promised, and we're now moving or exploring the space of generative models a bit more, and so now we're going to talk a bit about generative adversarial networks, or GANs. Okay, so let's look again at the VAE, and so we can say, okay, what is actually like our generative model in the VAE? So the encoder, like the thing that we're predicting, some latent code and all this stuff, like if it's not really necessary in order to like generate new data. So when we said, okay, this is just to shape the latent space roughly, and now we know, okay, in the latent space it's going to be Gaussian distributed, and we'll sample. So now you say you want to generate a new image, you just sample some kind of code and then you decode. And so really what you have for a generative model is just some kind of Z, but which we knew is just noise, right? Because then it's kind of reparameterized. And then, we decode it. And so like a valid question that you could ask is, okay, is all of this stuff really necessary in order to kind of train like a generative model? We could say, okay, this is our generative model. We go from noise to our data. It's somehow kind of parameterized, and let's just learn the parameters. Okay, so the problem with this idea is that, okay, if we want to kind of directly train this generative model, we don't really have a clear handle how to judge it. Let's say you have just something that spews out data. You put in noise, it spews out something. So how do you judge whether or not it's any good, right? And so it kind of produces samples using some kind of function of noise, right? But we don't know what the density is, because the thing just gives us the samples. So we don't really know whether or not the density that is kind of implicitly implemented by this function that takes the noise to the data, is anywhere close to the true density of the data that we have as training data, right? And so for both things, we don't have any values P of X, we only have samples, right? And so this is kind of what makes this very straightforward idea difficult. And so neither kind of the reverse KL nor the forward KL is really going to be tractable, or we can also not really produce any bounds. And so this idea kind of has a lot of problems to begin with, right? And so you can ask, like, do we give up? Okay, then the lecture would be over. Of course, we're not giving up, because actually it turns out machine learning gives us all the tools that's in order to handle a situation where we don't have a likelihood and we just have samples. So like beginning from statistical learning theory, where we have samples that we assume come from some distribution, but we don't know what the distribution is. We only have samples. And we built up all of machine learning like within the setting where we only have samples. And so we can use all of this, these tools that we have in order to train generative models as well. Okay, so let's kind of zoom out and we started from scratch, right? Okay, so let's say we want to have something that produces random things, right? And so as we've seen, basically a good way to do it is to do like reparameterization. We just take some noise, which comes from some fixed distribution, like a normal distribution, uniform distribution, doesn't really matter. And then we're going to stick it through some very complicated function, right? And then it's going to produce some x. So this function implicitly induces like a distribution p of x, right? But depending on what the function is, this will change the distribution. And so let's say we want to generate, or we want to tune f of epsilon so that it produces data like this, right? Okay, so how do we go about this? Basically, we can say, okay, I have no clue what this function should look like. I don't know. So, but I know in machine learning, I have like universal function approximation. So I know, okay, it needs to look somehow, right? So I'll just like assume a family of functions, and then maybe somewhere in this family, there's like a good function to generate this data. And so I just, create like a neural network that basically encodes this family of functions. And now I stick my noise through it, and this is the data that I get. Okay, so basically, there's a good generator of the data that I have. So it's definitely generating some data, but somehow like, okay, it doesn't really do the trick, or doesn't do what we want, because the data that it generates is crap. Okay, it's maybe not surprising because we randomly initialized the function. There's like, we didn't really communicate to the function, that should look a little bit like the samples that we have. And so it's just like some random like garbage in, garbage out. Okay, so now, but now we can ask yourself, okay, so you probably also would say, okay, this is a crappy generator, but why is it a crappy generator? Does anybody have an idea? How did you figure out that it's a bad generator? Yeah, so the data looks very different to the. So basically, what you're saying, it was very easy for you to differentiate between the green points and the orange points, right? So like internally in your brain, you wrote like a discriminative function that knows how to discriminate these two point clouds. So basically, okay, so the way that we know that it's a horrible generator is that we just look at it, and it's super, super easy to distinguish real samples from generated ones. So if you would set this up as a classification problem, like, it's very easy for you to do this classification. If I ask, okay, which one of these points are the fake points, you could immediately, give me an answer. And so not only can you do it in your brain, but you could probably even teach a computer to do it using all the tools that you learned in this lecture. Right, and so how do we do this? We just basically take a neural network, and we train a neural network to differentiate between real samples and fake samples, right? And so how do we do this? With binary classification. We have, our real samples is our training data. We have our crappy, horrible generator, and so we have now labeled data. So we know this is real data, this is fake data. We have, and then we can train binary classification, and so we know how to train it. We train it using binary cross entropy as a loss, and then it will find like a decision boundary the same way, all the way back to the perceptron and days and so on. We can make this classification very, very easily. Okay, so basically, okay, how does this look like after training? We can basically see, okay, the loss function gives us also like a quantitative measure. How bad is it? right? So loss function, if like a discriminator cannot differentiate between, two classes of labels or two classes of labeled data, the loss function in the binary classification is going to be 0.69, right? So it's like 50-50 guessing, right? If the loss is super, super low, right, maybe 10 to the minus 5, that's going to be like a measure that it's had a very easy time doing this classification. And so the degree of how horrible how horrible the generator is somehow controlled by the loss value, the binary cross entropy. And so then we can also see, okay, once we train the simulator, we can also look at, okay, what, this distribution is super peaked, like in both directions. And so we'll basically, classify all the real samples as, having high probability to be a real sample. And then all the fake samples will figure out, okay, all of these things have a low probability to be, a real sample. Okay, so, okay, what can we do now? Okay, we already managed to write a generator. Great, just happens to be a bad generator. Okay. Then we found out it's a bad generator by, training a neural network. Okay, so now we have two things. We have our generator and we have a function that rates how horrible this generator is, right? And so what do? Basically, we make it less horrible, right? So it's very easy. So we figure out, okay, we have this thing that is, giving us the mark. Okay, how bad is the generator? And now we'll just say, okay, let's tune the generator to make it less bad. And so this is, our generator. So we have our generator has like some parameters. We didn't touch them up to now. We just initialized them randomly. But now we have our generated sample. So we get from noise to our generated sample. Now we have our new rating function, which rates how bad the generator is, which is our, trained neural network that is, distinguishing real from fake data. And, with this, we can basically improve our generator by making it less horrible. Okay. So then what could you imagine is it doing? It might do something like this. So if this is, but the neural network is kind of choosing a decision boundary to rate samples, as bad or not bad, right? And so like a kind of clever strategy as a, if you want to tune the generator, you just move all of your samples into a direction so that they get high probability to be real, right? And so you kind of fool the discriminator that you trained in order to make it think that these are good samples, right? And so you take our orange kind of samples, and when we tune our parameters a little bit to move them beyond the decision boundary and make them real. Okay, so then if you look at the distribution of what the discriminator thinks of these things, now it's going to think, oh, all of these things are real samples. Okay, so do you think it's a good generator now? Not as bad, but it's also not great, right? So how do you know it's not great? Because you can still discriminate between these things. And so now we can basically say, okay, this discriminator is fooled, right? But maybe we can train again the discriminator and say, okay, now try to discriminate the real and the fake samples. And it's still very possible, right? The decision boundary, the criteria it's going to use is now different, right? So the decision boundary is different, but it's still very much succeeding in telling apart good and bad, like real and fake samples, right? And so now we're back at this thing. Okay, now so with this discriminator, we thought, okay, this is a great generator, right? But this is not the only thing that can look at the data. So now we have a second discriminator, and now it still looks horrible. But now you can play this game multiple times. So now we had our generator, we trained our neural network to rate whether or not it's good. Okay, given this rating, we're now improving our generator, and now we adapted our discriminator again. And so now we can say, okay, let's try to improve the generator again. We're gonna take the same trick. We're gonna move all of the fake samples again to the real samples to be classified as real samples, like beyond the decision boundary. And now it looks like this, right? And so now you start having a hard time. So now it's not super clear. Is this like you will not, if I wouldn't give you the colors of the things, you would not be able to really tell which ones are the real sample and which are the bad sample. But this happens through like this interplay between like training generators and training discriminators. Okay, so this is what's called the generative adversarial network. Why is it called generative adversarial network? So you have this generator thing, but then you have basically like a adversary or like an opponent, and so the opponent is the discriminator. So one thing is trying to generate nice samples. The other thing is kind of trying to figure out which ones are fake samples and not fake samples. And so there are kind of two players that are in competition to each other, and they all try to basically, the discriminator tries to prove, okay, your samples are fake, and then the generator tries to produce samples that are very difficult to recognize as fake, right? That's a very, very elegant idea. And so you can basically, by just playing this game for a long time, the idea is that you will basically get to a nice generator, right? Okay, so then you basically go here, and then at the end you have your nice generator, because now like it doesn't really matter how you can try to still retrain the discriminator, but it's not going to have a nice time doing a good job. Okay, so basically sometimes people describe this as like an artist that is trying to fool. So like in the art world, you have people that are rating images as real or fake, if you have like a fake Picasso or something like this. And then of course you have the people that produce fake Picassos, right? And then they're like in a competition with each other, and you're trying to basically figure out who is like a forger and who is like a actual what is an actual painting by Picasso, right? And so this type of game happens in the real world, and you have like the games between two agents. And so this is then easily described using game theory, right? We will not go into this, but if you have heard about the Nash equilibrium and so on, this is kind of what's relevant here. Okay, so let's say what kind of game are we playing? So this is a class of games called the Minimax games. And so why is it called a Minimax game? Because basically, okay, the discriminator is trying to minimize a loss function, right? That's basically we want to get good at discriminating, right? And then what the generator tries to do is it tries to counteract. And so how do we compute this loss function? We have like our standard binary cross entropy. We have the log probability for the samples that have label 1, and then one minus the log probability for the samples that are labeled 0, right? And so the loss function looks like this. You can clean it up a little bit, and then you can see, okay, you have these two terms, and the generator, so this one is trying to minimize this thing, right? The generator is trying to maximize this thing. So the discriminator tries to make the discrimination very easy, and so it's trying to decrease the discrimination loss, right? Because lower loss means better discrimination. And now the generator is trying to maximize it. Say, okay, I don't want you to, be able to have such a low loss function, loss value. I want to increase it, right? And so it's the same loss function here, but the difference is just, okay, one is trying to minimize it, the other one is trying to maximize it. You can still clean it up a little bit. You can kind of recognize, okay, here you're trying to, for the generator, you're trying to optimize the generative model, right? And so it doesn't really, so for when you're optimizing the generator, the discriminator is fixed, right? So we're operating against a certain type of discriminator. So it's like our turn, right? And now this discriminator is fixed, and we try to improve and fool this particular discriminator. And so this really doesn't depend on the parameters of the generator, so you can kind of remove this, and now you can kind of see what the loss function is going to be, right? And so all of these are not complicated formulas. It's just if you wanted to code like a generative adversarial network, which we might do in our exercise. Okay, so now you can combine this. So the discriminator sees this loss, and then the generator sees like part of this loss, the part that actually is affected by the parameters of the generator. Okay, so we can set up this game, and you can see that also in the discriminator, the generator loss plays a role. And now that you can see kind of why it's called like a minimax game, because we want to find the best generator, minimal discrimination loss. But we want it to be minimal when it's judged against the best possible discriminator ever, right? And so you have like the thing that kind of maximize, like among the family of discriminator, we have the thing that is maximizing the loss the most. And that loss we want to minimize using our parameters of the generator. And so that's called minimax game. Okay, so then if you kind of find this minimax solution, so let's not worry about how we find it, but if you find it, you can do some math, which I'll not go through in detail, to basically show that the solution of this minimax game, right? You can kind of see what the solution for a binary, like the optimal solution for a binary classification problem is related to the likelihood ratio, which we I think discussed, when we discussed binary classification. And you can stick in all these things, and in the end, what comes out is you basically okay, this maximum of the loss function corresponds to the symmetrized KL divergence between two distributions. So you have the fake and the real distribution, and you can compute the KL divergence in two different ways. Okay, you don't know which one is best, so maybe you can take the symmetrized version, and so this is what's called the Jensen Shannon divergence. It's like the symmetrized version of the KL divergence. And so now you say, okay, this inner term, the max L, corresponds to the symmetrized KL divergence, and now what we're doing with the generator is we're tuning our generator parameters in order to minimize this KL, the symmetrized version of the KL divergence. And so that's exactly what we want to do with the generative model. We want to find good parameters so that the true density and the fake density are not we're not able to tell them apart. Yeah.
Because in the beginning of the course we said that we are unlikely to find probably.
Right. Exactly. Yeah. So this is like this is the problem. Exactly. But in principle, like let's say you're able to solve this minimax game, like you would arrive at a solution where you will not be able to tell these things apart. Okay. So then, GAN started in 2014. So remember, like the history of machine learning. So the big breakthrough for deep learning was 2012, and so people came up in 2014 with this type of elegant idea of having two neural networks basically fighting each other. And so then there was a huge expansion of quality. So it started out with something like this. This is something that you could also code in your computer, and in fact, for things like MNIST, you can just do this thing on the computer, and then it became more and more sophisticated. And so within 4 years, you had like this. Not only did the images get larger and higher resolution and so on, but also, I mean, the quality of the generated images is very, very high, and you're not going to be able to tell apart kind of on a glance whether or not this is like a real person or a fake person, right? So all of these persons don't exist. With the left-hand side, maybe it's easy to imagine that this doesn't exist because it's not a photograph. On the right-hand side, I mean, it's already pretty difficult. And so there was like a period in deep learning where every other paper was like a new GAN paper, right? And so this was really, really popular. But as you said, it was always very difficult to train. So there's not only, it's one thing to have like this idea, and then there's a huge amount of engineering to actually make this work and make it converge and so on. Of course, this is also what started all of this discussion about deep fakes and so on, like all this generative modeling. I mean, by now it's almost like a lost cause, right? But I mean, once people found this, this really jump-started this discussion about, okay, can you trust the image data on the internet? Okay, so back to your question, optimizing GANs is very tricky. So why? Because you're not trying to find like a global minimum even, right? So actually what you're looking for is like a saddle point, and it's going to be super, 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 sensitive to any type of perturbation. So you're saying you have like your minimax gain, right? And so you want to say, okay, the maximum loss, so this is the loss function, and so the discriminator is trying to minimize this loss, right? But then the generator is trying to maximize it, right? And so let's say you have like these two, the dimensions, which are the parameters of the neural network. It will basically, okay, one thing, you're trying to sit in the saddle point, right? And so you want to optimize, explore this loss landscape, and then, you don't want to fall off like in either side, right? And so that is very, very easy to do. And so this is what makes learning generative models very complicated, or at least GANs. And so the way that we do this is that instead of fully, always saturating everything. So we, like when we discussed the idea, okay, we say, okay, we have our fixed generator, we train it to like discriminate as best as it can, right? And now we start fooling this. And so by this will very quickly basically move you into a direction which is hopeless. And so what we're going to do is we're gonna alternate, but we'll only train it a little bit. So the discriminator is going to be a little bit better. And now we're gonna start fooling it. But because it's not like super highly optimized, we might have like an easier time fooling it at this stage. And so then we try fooling it a little bit, and then we try improving the discriminator a little bit. And so you just alternate with a few steps, right? It might even just be one step, like one step of gradient descent, right? And then you're, flipping back and forth. And so this avoids falling off the saddle point. But it's still difficult, and so the difficulty is basically also, shown in this thing. So what we have in like standard machine learning, where we're trying to find like a minimum and not a saddle point, you have like all the gradients point to the minimum, right? And this is what's called a conservative gradient field, right? So you have like a source or a sink, and then all the gradients point to this thing. And it's a bit like, in the sun, you have a conservative force. It's all pointing towards the sun. And so here, with the saddle point, you have a non-conservative gradient field. And so you start kind of spiraling through this loss landscape. And so you might never actually converge. And so this is very complicated. Okay, so then what you might see is like this oscillatory behavior. You can, yeah. 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 So like in the saddle point, so the gradients, if you like would plot the gradient field, it's not going to be all pointing to the same thing, because there's some directions are pointing outwards and some directions are pointing inwards. And so if you would try to, so like a conservative gradient field is a gradient of like a scalar function. Yeah. Right. 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 Right.
So to me, it looks like
right. Yeah. Yeah. So I mean, so but the structure of this, so you're like either you're like in the bowl or you're on the saddle point, right? And so in the bowl, like the gradients will always point towards the thing. You have like guaranteed convergence if you're doing gradient descent, if you're at least within like the convex part of the loss function, right? And so in this saddle point situation, you're not in this bowl, and so the gradients are not pointing all in the same directions. They point in different directions, and so that's why you get these divergent things. So if you so this is not actually like a gradient field of a saddle point, but if you would have like a saddle point, you have gradients that point into like opposite directions, and then yeah. Okay, so what you can see then, for example, is some convergence issues like this. So it might be that, okay, you have like this. Okay, so if you go back to this like cartoon that we had. Oops. Right, so now we're so I always, of course, like in order to make the point, I move the samples in like a nice direction, right? But I could have also fooled the generator by kind of putting the orange dots like at the lower right-hand corner or something, or like the right hand in the middle, right? And it would still be bad. And so it might be that because you can always kind of fool it, but you'll never get anywhere. You just oscillate. You have like a great generator for this one discriminator, and then you fix it and so on. And so you'll never really start converging. And so this was a very idealized situation where it's like magically they appeared at the right position. And so you can get the super oscillatory behavior and it will just not converge. And so it's not like, so normally in machine learning, you watch your loss curve. If it's decreasing, great, you're happy. And here you have like a situation like the loss is not necessarily going to decrease, right? Because you're like in this minimax thing, you actually want the loss to be, 50-50 guessing, right? But it should be 50-50 guessing, not because the discriminator is crap, but because the generator is good, right? And so it's very difficult to assess, what the quality of these things is. There are a couple of other failure modes. So there's some things that kind of roughly look right, right? But then if you look more closely, they're really bad samples. And so you can have things. So you could imagine, okay, if you have like a discriminator that was trained on cats and dogs and so on, like I'm not surprised that maybe it cannot really recognize that this is not a dog because it doesn't really understand what is the dog anyways, right? It maybe has like a fur detector, and the fur detector on the left hand side will say, yeah, great, this is fur, right? But whether or not this is semantically a dog doesn't really, maybe it will not pick up like this. And so the discriminator needs to be really good. You have things like with multiple heads, and so this is still a problem with generative models like diffusion. You have things like where you have people with like 6 fingers or 7 fingers and so on. And so this is just because the thing doesn't really know, the semantics of it. There's also a thing where, so then the people ask, okay, how can I actually figure out whether or not it's a fake image or a real image? And so here I said it's already very difficult to tell. But if you look more closely into these things, because it doesn't have any semantic coherence, sometimes it will generate like some feature on the one side of the image and not on the other side of the image. And like one of the famous examples always earrings, right? So we'll like generate an earring on one ear and then not on the other ear, right? And so for like a person that, or like for a discriminator, this looks like a fairly good image, right? But then you have like some kind of prior beliefs about how likely it is. So in the 80s, maybe this was more probable, now in the 2020s, okay, maybe it's coming back, I don't know. Yeah, so these are kind of failure modes that you have. There's also a thing called mode collapse. And so there's kind of like a trivial solution to fooling the discriminator. Let's say you're able to generate one image. So you can generate this one image extremely well, right? And you'll just stick with this image and you'll basically always fool any generator, right? So you have like your fake image, right? You figured out, okay, I can generate one great fake image. And so whenever you pit this fake image against a real image, no matter how good the discriminator is, it will not be able to pick it up, right? Because it's not keeping track that you always like produce the same image, right? And so this is called the mode collapse. And so basically, there's like a true data distribution of images, like in the training data. And so you figured out to kind of generate one single thing, and then you just stick with it, and you picked out one mode. And so now you can try to mitigate this by trying to say you force, some type of randomness or variance and the creativity in these generative models, and don't allow it to just always produce the same thing. And so this doesn't come purely from the GAN loss function. You need to add like additional losses. So now again, you need to regularize the same way we needed to regularize with the BAE in order to fix this thing, right? So because this is a totally valid solution. Okay, so then the last thing is then basically, okay, we're still optimizing you in gradient descent, and already the optimization is difficult because we're like not in this kind of minimization, like global minimum thing. We try to find like a saddle point and so on. But there's a different problem that you can kind of imagine that this works, like at the late stage, where you already can produce images, and then maybe maybe the distribution of colors is not correct, so you're trying to fix it a little bit. but how do you even get started, right? So like if you just initialize a random number, like a random generative model to generate MNIST digits, like 28 times 28 pixels, okay, your generative model is going to look like the thing on the left, right? And then the thing that you want to have is the thing on the right. And so that's actually, I trained this, on the train yesterday. So, okay, so now, okay, what do you do? So like it has a really hard time going because I mean, there's no direction of who's going to tell you in which direction are you supposed to improve the generator in order to make it look more like this, because it doesn't look anything like the true target data at all, right? And so the gradients are going to be 0 or very, very small. And so you don't know really how to get started. And so you only produce garbage. And so then there's like one trick that is another trick. So we had the reparameterization trick. And so now we have the log discriminator trick. It's a new trick in machine learning. Basically, what we have is, so we are trying to minimize this thing. So this was the generator loss. So it's basically trying to minimize, 1 minus the probability. So the probabilities of the fake images should be close to 1. And so you're trying to minimize the distance from 1. But you can basically say, okay, this is roughly at least kind of from the shape on, which probabilities are likely and which probabilities are not likely. It's kind of same as minus log. So log 1 minus x and minus log of x, they have kind of the same. So it's like high on the left-hand side and low on the right-hand side, but they have a different gradient profile. So here you have, like in blue, this log of 1 minus the probability. And so here basically you have, low gradients. And then if you take minus log, you have strong gradients at low probabilities. And so this is kind of, I mean, it's kind of diverging from the standards, like derivation of these probabilities and so on, but it's just like to get the thing started. And so this is very similar to what we had in the like VAE. So, I mean, you can derive it all like using statistics and so on, but it doesn't help you if the thing doesn't work. And so then people, it's very common in machine learning is they just start kind of staying within the spirit of the thing, but then changing all these different pieces so that it actually starts learning, right? And so here then there's not such a strong statistical interpretation anymore, but like at least it learns something. And so then, so if you look at this, you can basically see, okay, after the same number of steps with the log discriminator trick, you can actually see, already something recognizable on the left-hand side. It's still not perfect, and then the longer you train, the better it becomes. And here, it's really not getting anywhere. It has a really hard time training, right? Even though kind of the solution is there, like there's this saddle point is just very difficult to find. And so here, basically, what did it learn? So of course, it's not completely impossible to get going. Okay, at least okay, I need to get all of the surroundings to 0. And so it's kind of found this already, right? But then it didn't really manage to generate like numbers. And so now, if you let it train longer, it will actually generate nice numbers. Okay, so then the legacy. So as I said, so the GAN years are over. So most of the state-of-the-art generative modeling doesn't really happen by GANs anymore. There are much more powerful models that are used, and so since like a year or so, everybody is talking about diffusion models, and they're more similar to variational autoencoders than to generative adversarial networks. So actually, like they are practically variational autoencoders, but with a few nice tricks. And but it had a very big influence, and it is a very neat idea that you have these things, working against each other. And so this idea of regularization, or you basically, designing your loss function to, represent competing interests in what you want to have. This is, something that is staying, and we see it also in the VAE and so on. And the GAN is just one more example like this. And okay, so then what is also nice, so we compared basically the GANs and the VAEs, and this is kind of showcasing the trade-off that we have between likelihood-based generative models that are very easy to train. Like an autoencoder, you train like an autoencoder in class without any problem. You just stick it in. I mean, it's almost obvious. You say, okay, I have decoded data. I compare it to the data. I minimize this, and so this is very easy to train. But it's difficult to get really high-quality samples with this, right? And so with the variational autoencoder, you will quickly notice because you have like this KL divergence term, which is trying to kind of shape the latent space, kind of tends to produce blurry images. Whereas here with the GAN, because there's no latent space really. I mean, there's the latent space of the noise, but I mean, you're not trying to control what this is. And so here you have like super sharp images, and you're basically trading off like, some tractability for quality of the samples. And so the non-tractable models where you don't have the ambition to be able to compute P of X and so on, you don't try to do density estimation, are difficult to train, but they can, if you get them to train, exploit the full expressiveness of, neural networks, and then, you get much sharper images. Okay, so this is what we have. So we have GANs and VAEs. And so these are already two interesting generative models. And then the next lecture, we're going to swing the pendulum back, and we're going to go all the way to likelihood-based models with normalizing flows. Okay, thanks a lot. Any questions? Any questions on Zoom? Doesn't seem to be the case. Okay, then, yeah.
Any way to deal with these oscillations?
Yeah, so you can try to do kind of mess with the learning rates and so on, and if you have different learning rates for the discriminator and the generator and so on, you can try to encourage it so that it kind of spirals into this saddle point more nicely, but it's very difficult. Yeah, so there's no surefire way, and it's just a lot of engineering hacks, and like there's a lot of like hyperparameters you need to tune, and then for some it works, and then for some it doesn't work. So yeah, if you want to train a generative adversarial network for your research, like be prepared for a lot of pain. Right? Okay. Sorry. Yeah. Yeah, exactly. So this is the main use case in physics. I think I mentioned it in the last lecture. So let me see, we have a chat. I'm uploading the lectures and the videos. I realize maybe we're not having all of them online, so I'll try to do this now. So this is exactly what we use it for. So like our simulation is very expensive, right? For simulating particle physics collisions and so on. But we have great simulators, and so they are basically our source of true data or real samples. And now what a lot of people work on is, okay, can we speed it up in order to produce, have like a faster simulator? Yeah, exactly. So this is kind of roughly what we. No, so that's the problem. So then there's a lot of discussion. Okay, so now can you actually get more information? And so for a while, people were deluding themselves. Okay, somehow, okay, I train a generative model, like it will magically learn, what the simulator does. I can then throw away the simulator. I can get more like statistical significance out of. I can generate more information from the simulator than what I had initially. And of course, this is not true, right? So it's always good. So whatever the generative model learns is like always conditioned on the training data that you have. There's no more information, at least the first, or not more information in the generative model. It's kind of like a maybe like it smoothes out some things, so it's a bit like a kernel density estimate in that sense. Yeah, so it's not like okay, I can suddenly generate 100 times more simulated data and I mean somehow have free lunch. So this doesn't work. Okay, yeah, but I think like if you look at the slides from the last week, I think I mentioned this is one of the reasons also I think I mentioned because so Moore's law is still happening, right? So we still have more transistors per chip, but we cannot feed our standard simulators, because our standard simulators, they are designed to work on CPUs. But we cannot take all of these transistors and make faster CPUs. So since 20 years, actually, there's no way to make computers go faster basically for free, right? So in the 80s and 90s, it was a very strong, like the next year you buy a new computer, it's twice as fast, right? Because you had twice as many transistors, and it was just great. And so this is like over, and then people try to do like multi-core processors, and for a while, so this carried us from 2005 to like 2015, 18, and so on. But now you're also like reaching a limit with this. But in principle, like the number of transistors we can put on a chip is still exponentially increasing. And so the way to do it is, okay, if I cannot, get a faster processor, maybe I just make my simulator work on a different hardware. And so the hardware that we are talking about is the hardware of matrix multiplication. So if I can express my simulator purely as matrix multiplications, I can get all the transistors in the world and like build a chip that cannot do any useful computation other than matrix multiplication. But but then I can use a lot of the I can ride Moore's law for a longer time. And so how do I express my thing as matrix multiplication? I train a neural network to do it. And so this is kind of what people want. So like we're not imagining, okay, that's like the machine learning will magically give us a better simulator. We already know we wrote the simulator, has like all the physics, and it's not going to be better, but it might be faster, and so it might match the hardware that we have in the future. And so these are basically the main things that we're interested in. Yeah. Okay. So then have a great weekend. Yeah. Yeah, so we should put out like a doodle poll. So we had like these 2 days, the Thursday and the Friday, and so we'll send on the Moodle like a poll so that people can put their names down for whatever date they prefer. Okay. Yeah. Okay. Thanks a lot. Bye bye.